one of the things that you want to have an awareness of is that there is an entire electromagnetic spectrum. And when we talk about visible light actually makes up just an itty bitty, teeny weeny little portion of it. Visible light we're pretty much going to see somewhere right around this band here. It's not a very wide band. You can see that. I'll actually make that a little bigger so you can take a look, right? So the visible light that you and I see occupies the smallest of portions on the entire electromagnetic spectrum. Okay? Doesn't mean it's not important, it just means that it occupies a very small space in there. Now, what you'll notice is that on this spectrum, you're going to see a bunch of other types of energy. Let me say it a different way. A bunch of other types of electromagnetic radiation that you've heard of before. So way down here, all the way on the left-hand side, where we have a very long wavelength, so here's one crest, there's the other crest, there's the other crest. You see how long those wavelengths are? So when we have long, large wavelengths, we have a very low frequency. So at low frequency, we have our radio waves. We start at the lowest with AM, and then you move up to FM. Just above FM, you actually have television radio waves. Okay, so television radio waves are nothing more than a form of electromagnetic radiation. As you move up from these radio waves, you'll hit radar, right? And a little bit above radar, you actually have, before you get to infrared, right about here, you're going to have microwaves. And so there's my prefix for micro. Now there's a reason why we call it microwaves, because if we look down here, we're going to notice that this represents the wavelength of different waves at different intervals. And so one of the things that you're going to start to notice is that as we start to go up this chart, my wavelength is getting smaller and smaller and smaller. So the distance between the waves goes from being measured in meters, way over here, to eventually it starts to go down so that we start to see something like centimeters, nanometers, and eventually, man, look how tiny this is going to get. This is going to be 1/10,000th of a nanometer. So we go from very long wavelength to ridiculously short wavelengths. And everywhere in between, we see how our electromagnetic radiation will operate. Now, important tidbit. How fast does an FM radio wave travel in space as opposed to, let's say, an X-ray or a gamma ray or a visible light ray? And the answer is they all travel at the same speed. But you knew that they all had to travel at the same speed because they were all part of the electromagnetic spectrum. They were all part of this electromagnetic radiation. So what we're going to find is that the minute you say it's electromagnetic radiation, whether it's a radio wave or it's a gamma ray, right, or a gamma wave, it's still going to travel at 3 × 10⁸ meters per second. So your takeaway from this, what you want to make sure you're clear about, is that there is an entire spectrum there, and all of these forms of electromagnetic radiation, or all of these forms of energy, all travel at the same speed in a vacuum. And what differentiates something from like a microwave to an X-ray is nothing more than the wavelength, right? The shorter the wavelength, we see that it's going to be further over here on the right-hand side of the chart. The longer the wavelength, then we're actually going to see it over there on the left-hand side of the chart. Now, one thing that you want to have an awareness of, you probably are not going to be asked to memorize this, but you want to have a concept of where things are. When we look at visible light, and you've probably heard this before, but remember in visible light the acronym ROY-G-BIV. Red, orange, yellow, green, blue, indigo, and violet. And the reason why I say that is that if you remember this idea of ROY-G-BIV, red, orange, yellow, green, blue, indigo, violet, red is lowest in frequency, violet is highest in frequency. And the reason why that's significant is because then you'll quickly figure out where at least 3 forms of energy are going to be. Just below reds, we have the prefix infra, below or within, right? So infrared, below red. And then just above my visible light, you have the prefix ultra, superior, above, better, etc., etc. So infrared, lower in energy than visible light. Ultraviolet, higher in energy than visible light. And so what this idea of electromagnetic radiation allows us to see is that we now have a way for energy to move through our universe, right? And we can transfer it from one location in space to another. But how does this relate back to our atom? How do we bring this back into the realm of chemistry? So as we look at this idea of electromagnetic radiation, the reason why it was so important to understand how it could move from one point in space to another is because now we have a method or a way to transfer energy between objects in space, right? So the next question that comes up that scientists start to look at, especially again as we go from the 1800s to the 1900s, is so when an object or a substance is absorbing energy, does it absorb energy in a continuous fashion, or does it absorb it in almost like a little incremental fashion? And so in our next episode, we're going to start looking at this individual by the name of Max Planck. And Max Planck is going to study this idea known as black body radiation. And so just as a little teaser and a little insight, black body radiation was really troubling to scientists. It was the reason why, for example, if you remember those old school stoves that used to have the metal rings on them at the top, right? And what would happen? You could turn it on low, and in theory it could be on low forever, and it would never glow red hot. But at a certain point, when you would just give it a little bit more energy, suddenly the whole ring would turn bright red. And so this is what was known as black body radiation, because it was like, well, obviously it's been receiving energy the whole time. Why did it start glowing when it hit a certain point, as opposed to if we just left it on long enough, shouldn't it eventually glow? So this is what we'll look at next time, and we'll see how Max Planck is going to come into our equations for not only energy, but we're then going to translate that back to the atom, and in particular the electrons within our atom. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.